All right, so coming up next, we have Lin Yan, who's going to talk to us about Roman high redshift transient science
with
Roman.
Right? Okay. Let me download that now. Okay. All right, so you can just click down. It's advancing, and then there's a laser at the bottom. Okay. Yeah.
Hi, my name is Lin Yan. I'm a staff member at Caltech. I will continue the theme of time domain science and talk to you about Roman high redshift transient science RISE project. This is a NASA-funded wide field science program approved in 2025. High redshift transient is really an exciting new research frontier, which will be made accessible by Roman. So here is an event which beautifully illustrates what exciting science with Roman will have in the next few years. As Maggie's poster presented yesterday, this event, SN 2024-WNY, is a redshift of 2 hydrogen-poor superluminous supernovae strongly lensed by foreground galaxies into 5 images as shown in this figure. Superluminous supernovae is 10 and 100 times more luminous than a typical type 1a or core collapse supernovae. Such high luminosity feature makes this class of events very likely detectable by Roman at high redshift. So what's an interesting question is these high redshift superluminous supernovae may behave differently compared to what we know at low redshift. This point is highlighted by our extensive follow-up observations of this event, 2025 WNY. And this work is led by Maggie Lee, a graduate student at Caltech. And our paper concluded that this event is indeed extremely unusual compared to what we know at low redshift. For example, it has extremely high temperature as shown in this diagram. And it also has extreme excess in far UV emission, both in continuum as well as spectral feature like here. So what's really the interesting question is whether this unusual feature is just for this particular event or for the entire population at high redshift. This question really will be answered once Roman gets launched. So what is RISE? RISE, as you just heard from Jacob, rapid basically finds transient in a single frame. RISE aims to search for fainter and higher redshift transients by using stacking method. And then our goal is to produce a production pipeline based on the rapid pipeline, and the goal is to release faint and high redshift alert streams to the public. The fields that's suitable for stacking, basically we aim for any fields that have multiple images. And for example, the high latitude time domain survey will have many hundreds of epoch observations over this 5-year survey time. So it provides the great data set for this exercise. Now, how deep can RISE reach? This figure shows the 5 magnitude limit as for a stack of, for one frame, 6, 18, and 50 stacks. As you see that in the H band, at the 6 frame stack, we can already reach magnitude of 20.7, the whole magnitude deeper than the single frame. And these two figures basically shows the predicted J-band light curve for pair instability supernovae and superluminous supernovae at redshift of 5.8. As you see that both these events can be detected in the RISE 6 and 18 stack. Anya has talked about also the expected number of high-Z events we will see. And this figure basically gives a summary of various types of supernovae, including normal core collapse supernovae, as well as very exotic events such as superluminous supernova and pairing stability. Basically, you can see you reach many thousands of events for normal supernovae, but for exotic events, we're seeing many tens of such events. We have started developing the RISE pipeline. Joseph Santana is a postbac working with us, and he has done some fantastic work in these initial testing. We basically, the image stacking method, we will be using OAgent software developed at IPAC, and the quality of the performance is pretty good. And then another important testing he has done is that he has run through the stacked images through the image subtraction pipeline, and we are able to recover simulated faint transient. So the next really important item we're still being intensively studying is actually how to derive the point spread function, PSF, in the stacked images. This issue is quite relevant for both image subtraction as well as point source photometry to get more accurate photometry. And currently we're testing both methods of deriving effective PSF from the stacked images, as well as compute the average PSF considering different PA and the SCA. And this is ongoing work, so more updates in the next few months. There's one more item, this big item is the alert stream. So far, this is really in the initial stage. We have not, I don't have more to say about this, but this is a to-do item. I want to spend a little bit time talk about post-alert characterization. So this point is really to provide an effective way for users to focus their resources on the high priority targets. So this set is that we have actually approved Cycle 1 program. I think Anya is also co-I on this program. PI is by Ori Fox. And then the idea is that we will take the RISE alert sample and supplement with characterization parameter, which will be derived from the machine learning software. And these parameters will include host galaxy photo Z, as well as the force photometry light curve, the color magnitude phase space of the transients, as well as the light curve fits, the model fits to characterize these. And furthermore, some of the training data set will use the low redshift transient samples, large sample from ZTF, and as well as the JWST high Z studies, as Anya mentioned before, which is somewhat limited in the light curve coverage, but we will use some of the lessons we have learned from there. And hopefully these characterization parameters will be useful for general users. Here's my conclusion of this talk is that high redshift transient is really exciting frontier for the next few years. And RISE is here to provide the help. We hope you can do the exciting science with the RISE product. I will take questions.
All right, thanks, Lynn. Yeah, questions for Lynn. Yeah, let's go right here.
Thank you for the talk, Lynn. Question, why is it so important to push the redshift frontier and the magnitude frontier as well?
So in many sense that for core collapse supernovae, we believed it's essentially the death of massive stars. Mm-hmm. And the massive stars at the high redshift, it's impossible to study them individually. So one of the ways to look at the high redshift, how stellar population evolve at high redshift is in some ways is through supernovae. So that's one reason. Mm-hmm. There's other reasons is that for example, the progenitors of superluminous supernova or electron-positron pair instability supernovae, there's been the model theory is speculated that these events are from extremely low metallicity massive stars. And these stars should be very abundant at high redshift because high redshift environment tend to have low metallicity. Mm-hmm. Stars will generally have lower metallicity. So where the theory at least is expecting to see these supernovae explode at high redshift. So all these are still a model. So we want, basically Roman will be first time to provide observational evidence with a large statistical samples to confirm whether our theory is correct or maybe need to be modified.
Okay,
so
great.
That's kind of short answer to
no, good answer.
Question. Yeah.
Thank you.
All right, more questions for Lynn. All right, I guess I have a quick question. So on the stacked image signal-to-noise plot that you're showing, it looks like it plateaued at around signal-to-noise of 10 at 6 stacked images. I'm wondering if you can say any more about that.
So I think the issue there is that we may be the noise. This is using this open universe simulated data. The noise may be characteristics when you reach 6 and 8. They're not. It's not behaving as what we expected, but I think the difference is small. There are some errors in those measurements there.
All right, if there's no more questions, let's thank Lynn again.